Okay, hello everyone. Let's go ahead and take a look at sequences. Now we're going to skip a little bit and, not skip, but we're going to jump a little bit from improper integrals and we're going to move to sequences. Now of course the reason for that is because sequences are the basis of what series are. And we know that a sequence is going to be written as such, and it's going to be a list of numbers in a definite order. Now we've dealt with arithmetic and geometric sequences, but there's so many different types of sequences out there. And we need to be able to go ahead and analyze them to, again, determine whether or not they converge or diverge, because that will have some consequences later with regards to the series. Now there's just a couple of limit theorems that we want to go ahead and pay particular attention to, and it's this one here. It says, say for example, you have three sequences, and a sub n is going to be less than b sub n, is going to be less than c sub n for all integers n. And what we're going to do then is, if we go ahead and take the limit for each one of those, okay, then we say that the limit as n approaches infinity of a sub n is approaching a particular value L, and if we know that the limit as n approaches infinity of c sub n is also going to be equal to L, then basically what's left is that this has to also converge to L. And this is going to be called the squeeze theorem for sequences. Okay, now there's a particular definition as well that's going to be important for us to know. It says a sequence is bounded if there exists a real number n such that the absolute value of a sub n, okay, so those are all the particular terms of the sequence, is less than capital M for all positive integers n. So the result of that, of course, is that all convergent sequences are bounded. So that means then, again, let's think about what that says. It says that if you have a sequence that converges, it has to be bounded. Now, what's not true is that all bounded sequences converge. That is definitely not something that we want to make a mistake about. And we'll go ahead and talk about those two in class. Now, of course, what we're trying to do is we're trying to just, again, determine whether or not a particular sequence converges or not as n approaches infinity. So in other words, if you have all of these terms that are generated, then does the terms actually converge to a particular value? So let's go ahead and take a look at, say for example, a sub n, which is going to be 1 over n plus n to the third. If we take the limit as n approaches infinity of that particular sequence, then notice that what happens is that this is just going to be 1 over infinity, and of course as this number gets larger and larger and larger, 1 divided by that huge number is going to be 0. So in other words, it is going to converge and it's going to converge to 0. So if we go ahead and take a look at a sub n is equal to n factorial divided by n plus 3 factorial, and we take the limit as n approaches infinity of a sub n, then notice we can simplify that factorial to just 1 over n plus 1 times n plus 2 times n plus 3. And again, we have the same situation where we have 1 over infinity, which of course is going to be 0, and therefore we say that this particular sequence converges as n approaches infinity. So again, what we're doing now is we're switching a little bit from improper integrals and series and taking a look at sequences, but still asking the same question as to whether or not sequences converge or diverge. And we know that we've actually seen certain certain sequences. We have certain limit theorems and theorems regarding whether or not a particular sequence converges or diverges, and in particular the squeeze theorem is one that's very nice. And we have a definition here regarding whether or not a particular sequence is bounded. And then we have a couple of examples there, and we'll take a look at some of those other examples later in class when we meet the next time. So we'll see you then. Bye-bye.